Okay, good morning, guys. What questions do you have this morning?
Number 10.
Number 10. Okay, so we've got this shape. First thing I'm going to do is I'm going to recognize that sine times cosine times 2 is 2 sine of 2 theta. That might make things easier. Okay, and we're going to take this shape and we're going to revolve it around the x-axis, which means you spin it all the way around. So we're going to have sort of a, it's not really a sphere because this sort of comes to a point on the sides, but it's going to be a mirrored shape with circular cross sections here. We get that if we spin it around there, I'll have circles as my cross sections. Okay, so we're going to take this representative rectangle, and they kind of drew it in there with that red line a little bit. So I got this slice, and I want the top point and the bottom point for sure. This is going to be at x comma, this is equal to 8 sine of 2 theta. Okay. Now this is going to be at x comma 0. And then how do I get the area of this or the volume of this cross-sectional piece? Well, if I take it out, that's a circle, and the radius here is equal to the change in the y values. So how far is it from the top of this to the bottom of this? Well, that's going to be 8 sine of 2 theta minus 0. So the volume of this little disc is going to be 64 sine squared 2 theta times pi, right? Pi r squared. And I want to add those up. And it's going to go from 0. Well, it's going to stop. Does it tell us where it stops? It stops at pi over 2. And then 64 sine squared 2 theta pi. Okay. And so are we good with the setup at least? The integral itself is a little tricky.
Yeah, I got the setup now.
Okay. Okay, so let's see how we do this one. There's a couple ways we can do it, but the easiest way, I think, is I'm going to take one of the sines of 2 theta, And I'm going to turn it, well, I guess I have to take both of them. How should I think of this? Well, the half angle identity. I got thetas there, so I'm going to use x. Sine squared of x is equal to 1 minus cosine of x over 2 over 2. All right. No, it's the other way around. This is 2. Okay, I think there's one of your half angle identities. The other one is that the cosine squared of x is equal to 1 minus plus the cosine of 2x over 2. Well, I've got a sine squared here. So I'm going to replace the x here with 2 theta. And this whole thing then is going to equal the integral from 0 to pi over 2. 64 times 1 minus the cosine of 4 theta over 2 d theta. I didn't put in a d theta up here, but I need a d theta up here, and I need a pi, right? Got the pi. And now I don't have to integrate a sine squared anymore. I just have to integrate a cosine, and that works out well for me. So this is going to be 0 to pi over 2. I've got pi times the 64 over 2 turns into a 32. I've got 1 minus cosine of 4 theta, d theta. So it's 32 pi, integral 0, pi over 2, 1 minus cosine of 4 theta, d theta. 32 pi. The antiderivative of 1 is theta. The antiderivative of cosine, cosine's a decreasing function, but it's got positive values, so I should have sine. So minus sine of 4 theta over 4, evaluated at 0 and pi over 2. So I put 0 in there. Sine of 0 is 0. 0 theta at 0 is 0. So the 0 doesn't give me anything. The pi over 2, I'll have 16 pi squared. And then I will have minus, well, the sine of 4 pi time, well, 4 times pi over 2 is just 2 pi. Sine of 2 pi is 0, so that's 0. So I don't have to even worry about that. So I just get 16 pi squared. Hopefully I've done all my arithmetic right. There we go. Okay, where do we have questions on that one? The integral was kind of the tricky bit that time because you needed a trig identity.
I was honestly struggling to set it up.
Okay. We're good with the circles then?
Yeah, for the most part.
Okay. Other questions you have today?
Number 23, can we look at that one? Writing it like all in one integral is what I'm struggling with.
Okay. So let's draw the picture. First quadrant above x squared. Oh, above by x squared, below by the x-axis. And then on the right of the line, x equals 3. So that's the right side, the bottom's the x-axis, the top's the x equals curve. And then we're going to revolve it around the line x equals -1. And we only want the volume in the first quadrant to be rotated around there. So this is the thing that gets rotated around this line. So I'm going to erase this part of the parabola so it doesn't screw up our picture as much. And so there should be sort of an empty part here. And then this figure will have either washer-shaped figures, cross-sections if I go horizontal, or I think the better idea is probably to go vertical. So let's draw that again. If I take a representative rectangle here, and I rotate it through, you get sort of tube shaped pieces, right, that are dx wide, and however tall the rectangle is, and then the radius is this distance from x equals 1 out to the point. Does that make sense? Maybe that pink's not a good color. Let's go green. Okay, so the bottom point here is at x0. This point is at x comma x squared. This point and this point that are going to kind of help me figure out my radius. These are at -1 x squared and -1, 0. Right. And then that should give us everything I need to figure out the volume of this bit here, right? It's dx wide, so I'm thinking I have this pipe that's just barely wide. And I'm going to unwrap it. Like if I cut it down the middle here and unwrap it, it turns into a rectangle. And this will be the circumference of the pipe. So this will be 2 pi r, but the height's still going to be the same. And then the depth is going to be dx deep. So I want the volume of this thing is 2 pi r times h times dx in this case. So what is my radius? My radius is the distance from this point to this point, right? So that's going to be x minus -1, because the difference in x values this time gives me my radius. The x value at this point's x, the x value at this point's -1. That's x plus 1 equals the radius. And the height is going to be x squared minus 0, the difference in the y values. So my volume is going to be 2 pi times x plus 1 times x squared times dx. Are we good with that?
Could you go over where the bottom one came from again?
This one?
The one below that.
Okay. So we're good with the 2 pi. And then the radius we decided was x plus 1 because it's the distance from the middle, from where we're rotating out to where the point, the representative rectangle is. And so these have an x value of x. The center of the rotation has an x value of -1. The distance from x to -1 is x plus 1. That's my radius. And then the height is just the height of the rectangle, which is x squared.
Okay.
So now I'm going to integrate from 0 to whatever, 2 pi x plus 1 x squared dx, because that's the volumes that I'm adding up. Well, I start having representative rectangles here at 0, and I stop having them at x equals 3. And so I'm going to integrate one of these, I'm going to call them a shell, one shell for every x value between 0 and 3. You might think that you get shells for each of these rectangles over here too, but this shell and this rectangle and this rectangle, they both give me the same shell. So I'm only getting a single shell. I only want to add up the volume one time. So I'm only going to count the rectangles between 0 and 3. So I'm going to do the integral from 0 to 3, 2 pi. X plus 1 times x squared. 0, 3. Oh, it wants it. It has a dy here for me. Okay, so this is a dx. I need to do something different if I'm going to do dy. Okay. So if I look at these stack up in the x direction, right? I get different pipes. It's kind of like a Russian doll type thing where you've got a slightly smaller pipe inside of each one until they give you the entire shape. But they sort of stack up in the x direction. This integral that wants us to stack them up in the y direction, so I have to do something different. I have to draw a different picture because these shells, they don't stack up in the y direction. If I want stacking stuff in the y direction, I'm going to have to draw discs with holes in the middle or washer looking things. So let's draw a different picture. Sorry. Same setup though. Got x squared, x equals 3, x equals 0. X equals -1. X equals -2, back to x equals -5. That'll be the mirror image of this thing. And then if I want stuff to stack up in the y direction, I have to draw a horizontal line in there. Okay. And over here, I'll draw the corresponding horizontal line. I only have to stack these things up once, but what I get when I do this rotation is I get washer looking things, right? They're actually called annuluses or annuli. Okay. So I need to find an inner radius and an outer radius for this. So that's going to be a little r, and we'll call that one a big R. And the volume of this thing is going to be pi r squared, the volume of the big circle, minus pi r squared, the volume of the little circle. And then these are dy thick, so the volume of one of these washers or annulus is going to be that formula. So I have to figure out what capital R and little r are. Well, that means I have to label these points on my representative rectangle. They each have the same y value. This one always has an x value of 3. This one has an x value of the square root of y, because points on this curve, they correspond to x squareds, right? Which is the same thing as the square root of y comma y. I mean, I'm given the equation that y equals x squared. So if I want the x coordinate given a specific y, I can figure out that x equals the square root of y. And that gives me that point there. Okay, are we good with my picture in terms of y now, instead of everything's labeled in terms of y instead of x?
Yep.
Okay. So now I have to figure out capital R. Well, it's the change in the x values from here to here. Well, this x value is at -1 comma y. So the outer radius is always going to be 4. And the inner radius, that's going to be the one that changes. That's going to take the x value of the square root of y minus minus. So the square root of y. Are we good with those two radii?
Yep.
Okay, so the volume then, I'm going to factor pi out. Four squared is 16 minus square root of y plus 1 squared dy. So I'm going to have this integral from 0 to something. I haven't figured that part out yet. Sorry. Cough just wanted to sneak in. Pi 16 square root of y plus 1 squared dy. I have to figure out what that top bound is. So I'm going to come back to my picture. I start getting horizontal strips at 0. And I stop getting them at this point here. And that point is at 3, 9. So So I'm going to stop getting horizontal strips at 9. So this will go from 0 to 9. At 0 to 9, I've got pi. I've got 16 minus square root of, it doesn't like square roots, so square root y plus 1 squared dy. Okay. And then I integrate that. To do that, I'm just probably going to expand this thing out. There's not really a nice substitution, so I would just expand it out and then integrate. So let's do that quick. Factor out the pi. I have a 16. I have minus y plus 2 square roots of y plus 1 dy. So pi integral 0 to 9, 15 minus 2 square roots of y minus y dy. 15y, that turns into minus 2y to the 3 halves over 3 halves minus y squared over 2 at 0 and 9. Sorry, not, yeah, y squared over 2. Okay. So pi, plug 0 in, you get 0. If I plug 9 in, I get 15 times 9. The square root of 9 is 3. Squared or cubed is 27. So there's a 27, but I have to divide by 3, which brings me back to 9. And then I have to multiply by 4. So that's minus 36. And then I've got minus 81 over 2. Okay. So that's pi. 15 times 9 minus 4 times 9. Right. That's 11 times 9. So that's 99 minus 81 over 2. That's going to be pi 198 minus 81 over 2. 99 halves is 198 halves. So that's going to be 117 halves pi. Questions on that one? We set it up in 2 different ways. I didn't notice that it wanted the y direction way first. So. Questions on either of the setups? Both of those setups are good because that's basically what we're going to be talking about in 6.2 is these volumes of revolution. We'll do a lot more examples of them in 6.2. Other things you guys want to talk about this morning?
Can we look at number 19? I think it's kind of the same thing with the washer, and that's probably where I kind of got screwed up.
This one's the shell. because we're revolving around the y-axis and it's got this vertical strip drawn. I guess you can do it with either one. If you don't want to use the arctangent function, and I don't think I want to integrate arctangents yet because I don't have any idea what the antiderivative of arctangent is at this point in calculus. So I think we want to use the washers. Or sorry, the shells, not the washers. So here's our picture. And we're going to revolve around the y-axis. That's at 3. Okay. So if I draw in a rectangle, what I end up with is these sort of pipe looking things again. And so I'm going to need to know what the radius is and the height. Okay. So the volume of this thing is going to be 2 pi r h dx. Are we good with the volume of that little pipe shaped thing?
Yeah.
Okay, circumference and height, and then the width, the depth, or the thickness of the pipe. Okay, so I need to label some points here. Let's label that point, and then this point for the center of rotation. So that's at an arbitrary x value, and then 3 tangent x is equal to 3 tangent y. Okay. Maybe you're right. Maybe we do have to do washers because this has this all in terms of y instead of x. Okay. Because that's not x 3 tangent y, that's x is the 3 tangent y. So if I was going to label that point, I would label it as 3 tangent y comma y. All right, that's what that point is. And so because that's in y and because these would stack up in the dx, I don't want to stack them up in the dx direction and have everything in terms of y, because then my integral would be a bunch of y stuff and then a dx, and I can't do that because the variable of integration is x. I can't do it that way. So let's redraw this picture. Realize that everything is in terms of y. So that's at 3. This point's at 3 comma. Well, if I want 3 out, I want 3 tangent of y equal to 3. So this tangent of y equals 1. So y equals pi over 4. This
It
is
gave that
0,
part.
0. Sorry?
That part's on the y-axis. It gave it to you.
Oh, it is. Nice. Okay. But that's how you find it. Okay. And now we can draw in a representative rectangle. We've got everything in terms of y. So we're going to stack stuff up in the y direction, which means that I should draw my representative rectangles so that they stack up in the y direction. And so this is going to be a dy wide rectangle. This point is at 3 tangent of y comma y. This is at just 3 comma y. And then my radius here, the center of the circle, is at 0 comma y. So let's draw the shape. It's not a very circular washer, but you get the idea. So I've got inner radius and outer radius. Little inner radius, that's going to be the distance from here to here, which is going to be the change in the x's, which is going to be 3 tangent y minus 0. The outer radius is going to be from here to here. It's going to be the change in the x's again. It's going to be 3 minus 0, which is just 3. And so the volume of one of these little washers is going to be pi r squared minus r squared dy. So that's going to be 9 minus 9 tangent squared y dy. Good with that?
Yeah.
Okay. And so my integral is going to be 0 up to pi over 4, because that's where these start and stop. I'll put the 9 pi out front. 1 minus tangent squared y dy. And then I don't know what the antiderivative of the tangent squared is, but I can convert tangent squared to secant squared. So what's the relationships between tangent squareds and secant squareds? Anybody remember? Tangent squared plus 1 is equal to the secant squared. So if I have just tangent squared here in this expression, that's going to be the secant squared of theta minus 1. So that's going to turn into, if I want a minus sign on it, right, as I have a minus, I'll put a minus on the secant and I'll put a plus 1. So this is equal to 0 pi over 4, 9 pi 2 minus secant squared theta d theta, or y dy. Let's do y dy. Are we good with that? Just a simple substitution with the trig. Okay. Integral 0 to pi over 4, 9 pi 2 minus secant squared y dy. Antiderivative of 2 is 2y. Antiderivative of secant squared is tangent y. We're going to evaluate at 0 and pi over 4. At 0, y is 0. At 0, tangent is also 0. So the 0 side, I don't have to actually evaluate. The pi over 4, I get 9 pi. 2 times pi over 4 is pi over 2. Minus the tangent of pi over 4 is 1. So I get 9 pi squared over 2 minus 9 pi, which is 9 pi times, well, either way, factor it or expand it out. Okay. What questions do we have on that one?
I think it was just setting it up for me.
Yeah, figuring out how to draw these pictures and how to label them is really important, not just for this section and the next section, but for when we start doing applied problems and we start doing more stuff in Calc 2 next semester. Being able to draw these pictures of what you're actually integrating and which variable you're integrating, and sort of having in your mind or in the picture where these representative rectangles or representative strips are is important. So definitely practice this. And we'll get more practice in 6.2 as well. I think I've got time for like one more.
We look at number 12.
So y equals 3 times the square root of the sine of x. It's going to look like the sine, but it's going to be squished. It's still going to get up to 3 because the square root of 1 still goes up to 1. It's going to be kind of a weird shaped sine. Y equals 0, that's the x-axis. X1 equals pi over 6. X2 is pi over 2. Pi over 2 is going to be right at the top. Pi over 6 is going to be in here. And we want to find the volume of the solid generated by revolving this thing around the x-axis. So I want to take that part of the figure and I want to revolve it around the x-axis. So I'm going to have this volume here. It's going to look like a bowl with like solid stuff in the middle, right? Flat on the bottom. This is the bottom. Flat on the top, but solid stuff in the middle. Okay. And I think the strip that I want to do, get rid of that. Is vertical, and then when I rotate this strip, I get just discs that way, right? Put them back on their side. And that radius will be the height of this strip. Okay, so I'm going to label this point. This is at x comma 0. This point is at x comma 3 square root sine x. So the volume here is going to be pi r squared dx, because these things are dx thick. And so that's going to be pi times 3 square root sine x squared dx. So I'm going to integrate. I start getting these strips at pi over 6, and I stop getting them at pi over 2. Of the pi, which I'm going to pull outside the integral. I will have a 9, which I'm going to pull outside the integral, and then I'm going to have just sine of x inside after we square it, right? Are we good with the setup to get that integral?
Yep.
So this will be 9 pi. The integral of the sine is the minus cosine. I'm going to evaluate that at pi over 6 and pi over 2. Cosine of pi over 2 is 0. Negative 0 is still negative 0. And then I have to subtract off 9 pi times negative the cosine of pi over 6. Let me draw the triangle because I always forget about these. Pi over 6 is the thin one. So this is the short side. This is 1/1/2. This is the square root of 3 over 2. Cosine's adjacent, so it's the square root of 3 over 2. So it's the minus square root of 3 over 2. Minus and minus become a plus. That goes away. So this is 9 square roots of 3 over 2 pi. What I hit there. Where do we have questions on that one?
I was having trouble setting it up.
The setup. Okay. We see or figure out where you were having trouble and how to avoid it.
Yeah, thank you.
Any last quick questions? Okay, we'll do more of these volumes of rotation tomorrow. More washers, more discs, more shells. So I will see you guys in the morning.
Can I ask one thing real quick about our
Yep.
project?
Sure.
I was just wondering if, like, for the last part, I don't even know if I can ask this, but like, how far are we expected to go on that? Like for in finding them in terms of that, like, I have all the stuff that it said at the very least find, but
Right.
I don't feel like I'm getting anywhere farther when I'm making like attempts. Is that normal?
That's okay. I just need you to explain why you think there's probably not a way, or what the hurdles are and why you don't think you might be able to overcome them. Does that make sense?
Yeah. So, okay.
I'm not really expecting you to get too much more than what I asked for specifically. If you can, like, say something a little bit more, that's fine. There are a few things that you can say, but there's not very specific things that you can say further.
Okay. Thank you.
Yep.